Katie, do you want to learn about the Doppler effect today? The Doppler effect? Well, we're going to learn about the Doppler effect because I have a problem here. So, hi, Honors Physics. Today, you're going to learn about the Doppler effect, even if Katie isn't. So, this is actually the first problem that I have on our problem sheet that I gave you, that I pushed out in Notebook. So, here's what it says. A plane flying at half the speed of sound, and I give you that speed is 172 meters per second, emits a frequency of 5,000. Now, the second part of the problem I just condensed. It says, what frequency change will the stationary observer hear as the plane passes? What the problem says for you basically is, what do they hear as the plane approaches? What do they hear as the plane recedes? So it's the same problem. I just phrased it a little differently. So since this is the Doppler effect, we want to start with our Doppler effect formula. And our Doppler effect formula is the frequency heard by the listener or the observer is equal to the frequency emitted by the source times a complex fraction. The velocity of the wave plus the velocity of the listener divided by the velocity of the wave minus the velocity of the source. So there's a lot in that formula. A couple of things to remember. Your velocity of the source or the listener is positive when they are approaching. So if either your source or your listener is getting closer to the other, okay, that's a positive. If they are getting further away, they're going to be negative. The other thing to remember before you start the problem is we have a higher when we are getting closer together. Okay, your frequency that you observe will be higher if you're moving toward each other, and it will be lower if you are moving away. Okay? All right, so let's start to fill some things in here. First of all, my observer is stationary. That means that my velocity of my listener is going to be 0. That's throughout the problem. So now we want to know what the frequency change is going to be. So I need to know what was the sound of the frequency, the sound of the airplane as it approached, and then what was the sound as it moved further away. So let's start to plug in. So for my approach, the frequency that I observe is equal to my source, which is 5,000, times the velocity of sound. If you are not told, and we're not told in this case, we can take the velocity of sound to be 340 meters per second. So that's 340 divided by 340 minus the velocity of my source. Now, we're told that our source was moving at 172 meters per second. Initially, it is approaching us. So that means that it initially is going to be positive. So that means I'm going to say minus positive 172 meters per second. I'm going to hit all of that into my calculator, and I'm going to get a pretty big number. I get something like 11,000 when I do this. So yeah, I get 10,119. And my unit is hertz. Okay, so now I know the frequency that the plane had as it was approaching my observer. So now let's see what happened when we were moving away. The only thing that's going to change now is the plane is now moving away, so the plane's velocity is going to be negative. So 5,000 times 340 over 340 minus negative 172, which then becomes plus 172. So that's going to give me 3,320. Now, before I solve for the change, there's a couple of things I want to point out to you. Number one, notice when the plane was moving toward, its frequency more than doubled. When it was moving away, though, it's not half. It's actually about 2/3. When you're moving towards something, there is a greater frequency shift than when you're moving away. Okay, so that's just something that you can check. The other thing I want to do is I want to say, well, do I follow these two rules here? When it's moving toward, was the frequency higher? Yes, it was. When it was moving away, the frequency was lower. The other thing that I do want to say is we're moving at a really high speed here. Since we're moving at a really high speed, we're going to see a dramatic shift. If we're moving at normal speeds, like speed for a car, you're not going to see as much of a shift. But it doesn't take much for our ears to pick up that frequency change. All right, so now let's get the end of the problem. What frequency change will an observer hear? So the change in frequency that our observer is going to hear is going to be 10,119 minus 3,320. And that gives me almost 6,800 hertz. Our ears are capable of detecting differences of about 2 hertz, so that's going to really be very, very obvious. Okay, that's as much as I want to do on the Doppler effect. Solve the problems that I sent out to you. I do put some notes in the problems. Once you're done, of course, I will send you the correct answers. Look at those notes that are in the problems, and I hope you have a great day. Katie, I hope you learned something too. Did you learn about the Doppler effect?
I don't think so.